Welcome to Module 19, Engineering Calculations and Design Review. In this module, we focus on making calculations and design reviews defensible. A defensible calculation is not just a correct number. It has a clear boundary, documented assumptions, trusted measurements, consistent units, an appropriate equation, and a reasonableness check. A good design review does more than verify that a point list exists. It reviews the relationships among equipment, sensors, control logic, failure modes, operator response, and commissioning evidence. Our goal is to help learners make engineering decisions that another professional can understand, repeat, and verify. By the end of this module, learners should be able to define calculation boundaries, preserve units, identify trusted inputs, apply reasonableness checks, and review design intent as a complete system. This is about professional discipline. A calculation that cannot be explained is difficult to trust. A design review that ignores failure behavior can miss the most important risk. We want learners to document the path from field evidence to engineering conclusion, not just the final answer. This workflow summarizes the discipline we want learners to follow. Start by defining the physical system boundary. Then identify measurements and inputs, select the equations and methods, preserve units and conversions, perform a reasonableness check, review the control strategy, identify failure behavior and safety limits, verify through commissioning evidence. Only then make an engineering decision. The sequence matters because each step protects the next one from unsupported assumptions. Before calculating, draw the physical boundary. This can be simple. It may be an air handler, cooling coil, a hydronic loop, a chiller plant, or a single critical room. The boundary tells the learner what is included, what is excluded, and what crosses the line: air, water, heat, power, fuel, refrigerant, or signals. Many bad calculations start because the boundary was assumed instead of stated. If the boundary is unclear, the result may still have numbers, but it will be difficult to defend. A professional calculation separates measured, calculated, design, and assumed values. Measured values should still be checked for range, units, calibration, sensor placement, and operating condition. Calculated values depend on the quality of their inputs. Design values are useful for comparison, but they are not proof of current operation. Assumptions are not wrong, but they must be labeled. When learners present a calculation, every input should show where it came from and how much confidence the team has in it. Units are not decoration. They are part of the engineering logic. A common BAS failure is mixing units, applying a field formula outside its intended unit system, or confusing a temperature value with a temperature difference. Learners should write units on every line, convert before combining values, and check whether the final unit matches the quantity being calculated. If the formula expects gallons per minute and the trend is in liters per second, the result will not be valid unless the conversion is handled correctly. The best equation is the one that fits the decision, the boundary, and the evidence. Do not make a calculation more complex than necessary, but do not oversimplify when the decision is high impact. Coil review may use water side and air side heat transfer. Airflow review may use duct area and average velocity. Plant review may require kW per ton and total plant boundary. Moisture problems may require enthalpy or dew point instead of dry bulb temperature. When the consequence is significant, confirm the conclusion with a second method if possible. This worked example shows how calculations support a story. The air side sensible estimate is about 432,000 B2 per hour. The water side estimate is about 400,000 B2 per hour. These numbers are not identical, but they are close enough to be plausible, especially when we remember measurement uncertainty and the fact that the air side estimate shown here is sensible only. A professional conclusion should not pretend the calculation is perfect. It should state the assumptions and the confidence level. Reasonableness checks are the professional safety net. A calculation may be mathematically correct and still produce a conclusion that does not fit the real system. Learners should ask whether the magnitude is believable, whether the direction matches expected behavior, whether the operating state was steady, and whether a second method supports the conclusion. They should also identify the weakest input. In many BAS calculations, confidence is limited by flow measurement, sensor location, scaling, or whether a value was copied from design documents instead of measured. A design review should not be limited to equipment selection and point lists. It should test the relationships Does the selected equipment support the sequence? Do the sensors measure the variables the sequence needs? Do the actuators have authority to create the physical change? Do alarms detect the failure early enough? Do operators know what action to take? A strong review follows the chain from physical equipment to measurement, control logic, alarm response, and commissioning evidence. Failure behavior is part of engineering design. A system is not finished because it works under ideal conditions. Learners should ask what happens when a sensor fails, an actuator sticks, network communication drops, power is lost, data becomes impossible, or an operator override remains in place. The goal is not to imagine every possible failure. The goal is to identify credible failures, their consequences, detection methods, safe fallback behavior, and recovery steps. Commissioning should prove that the failure behavior works as intended. Commissioning verifies that the design performs under real conditions. The learner should prepare before testing, confirm that required points and safeties are ready, run functional tests, trend the system response, document issues, assign owners, retest, and close only when acceptance criteria are satisfied. This protects the owner, the integrator, and the operations team. Without commissioning evidence, a calculation or design review remains an unverified prediction. This scenario brings the module together. An air handler cannot maintain supply air temperature, the chilled water valve is often at 100%, and humidity complaints increase during humid weather. A weak investigation might replace a coil or raise pressure. A stronger investigation defines the boundary, collects airside and waterside evidence, verifies whether airflow is measured or assumed, checks humidity, verifies valve motion and authority, reviews reset logic, and defines a commissioning test. The learner should leave with a repeatable diagnostic method. These common mistakes appear again and again in BAS work. People use design flow as measured flow. They mix units. They ignore transient behavior. They trust one sensor value without checking location or range. They report a final number without showing assumptions or uncertainty. They review points but not failure behavior. The professional correction is to make the method visible. Show the boundary, inputs, units, formula, result, assumptions, reasonableness check, decision, and field verification. Best practices turn engineering discipline into a team habit. Use standard templates so calculations are easy to review. Maintain version control so the team knows what changed. Document assumptions clearly. Use peer review when the consequence is significant. Commission the result under field conditions. Then teach the finding so the next project benefits. In mature BAS organizations, calculations and design reviews become living knowledge, not one-time paperwork. To summarize, defensible engineering starts with the physical system boundary. It labels inputs, preserves units, uses appropriate equations, and checks results against reality. Design review connects equipment, measurements, controls, failure behavior, and commissioning evidence. The strongest BAS professionals do not just produce numbers. They produce decisions that can be understood, repeated, and verified. In the next module, learners will apply this method to a set of realistic case studies and an engineering workbook. The correct answer is B. If the calculation excludes pumps and towers, it may be valid as a chiller-only calculation, but it is not a total plant performance calculation. The professional response is to redefine the boundary, document what is included, and report the result clearly. This is the habit we want learners to build. The boundary must match the decision. If the decision is plant optimization, then the plant-level energy boundary must include the relevant auxiliaries. For the practical assignment, learners should complete a calculation and design review on a real or sample system. The submission should include a boundary sketch, input table, units, sources, calculation conversions, reasonableness check, design review findings, and commissioning verification plan. Recommended systems include an AHU coil, hydronic pump and valve circuit, chiller plant, boiler reset sequence, critical space pressure control, or sensor and actuator review. The purpose is to apply the method, not simply fill in a worksheet.